All right, so now we're going to talk about numerical methods for solving parabolic equations. And we're first going to look at explicit methods. So as you hopefully recall, a canonical example of a parabolic partial differential equation is the heat equation. So a canonical example of a parabolic PDE is the heat equation, or diffusion equation. Okay, which looks something like uxx plus uyy plus uzz is equal to ut. All right, so this is in 3 dimensions. We had sort of previously talked about it just in 1D. Okay, and it's understood that uxx is the second partial derivative of u respect to x squared, and so on. Okay. All right. So let's look at a simpler example, which is a 1D rod. So imagine you have a rod and you are trying to describe, say, from the interval from 0 to 1, and this is the x direction. Okay, then you want to know what the heat is along this rod. It's like with maybe some conditions on the left and the right, and so on, as well as some initial heat distribution. Okay, so let's think about what the solution looks like, right? So this is x, this is time, right? So so if you think about what you need to do in order to specify the appropriate initial conditions and boundary conditions in this, you have to have boundary conditions on the left and right ends, it's like of this rod. Okay, so you have it's like 2, this is from 0 and 1, right? You have an A of t, which is telling you the temperature sort of at the left endpoint, and B of t, which is the temperature at the right endpoint. And then you have some initial heat distribution, let's call that g of x, which tells you what the initial temperature is. Okay, so the way this is set up is something like the following. You have uxx is equal to u of t. That's the partial differential equation. This is true for t greater than or equal to 0, and x is between 0 and 1. All right. Then you have to specify a bunch of initial conditions. All right. So okay. So the notation here is u x of t. All right. Sometimes it's t of x, but here I'm going to do u x of t. So u x comma 0, so that's initial time, is equal to g at x. Right. So this is the initial heat distribution. All right, and you want x to vary between 0 and 1. All right, and then we have the left and the right conditions. So u for an initial point x equals to 0 for all time is given by a of t, and then t is greater than 0, greater than or equal to 0, and then u1t is equal to b of t, t greater than or equal to 0. Okay. All right. So that's sort of what's happening. It's like you specify the conditions on the initial time slice, right, and then the left and right endpoints for all time. Okay. And then you have this partial differential equation telling you how the heat is sort of diffusing. It's like over the rod. Okay. All right. So that's the basic idea. So let me just leave the equation, and I will erase the rest of it, and then we'll consider a finite element discretization. Maybe let's draw this in here. Okay, so 0, 1, this is x, and then you have the data at, this is g of x, then this is a of t and b of t, right? X and t. All right. Okay, so that's the setup. Okay, so I want to construct a finite difference method for this. Okay, so I'm going to again, this is u of x and t. So I'm going to write t j as j times some step in time, which I call k, and so j is greater than or equal to 0, and then x I is I times h, right? And then I goes from 0 to n plus 1. So k is the spatial, so actually it's the temporal step size, right? It's literally the time step. And then h is the spatial step. Okay. All right. Okay. So given it's like this data, right? So you expect that this is in some sort of lattice. Okay. All right. So I want to approximate the derivatives, right? So I want to approximate the derivatives. And we've seen how to do this. It's like using finite difference approximations. Using finite differences. Okay. So so we know, for example, that f prime of x is approximately 1 over h, f of x plus h minus f of x, right? And then f double prime of x is approximately 1 over h squared, f of x plus h minus 2 f of x plus f of x minus h. Okay, and there are of course many others. It's like, but I'm just going to use these two, and I'm going to use that to discretize the heat equation. Okay, so what this tells me then is that so I differentiate second derivative in space, right? So the spatial parameter is h. So you have 1 over h squared. Let's call it v, x plus h comma t minus 2v x t plus v x minus h t. Okay, so this is an approximation of u xx is equal to 1 over k v of x t plus k minus v of x comma t. This is an approximation of u t. All right. Okay. So so I'm going to look at. So I'm going to let x comma t be sort of xj comma t, or xi comma tj. Okay, and when I do that, I can rewrite this in terms of this kind of indexing notation, right? So tj is equal to j times k, and xi equals to ih. Right. So with that, right, this becomes 1 over h squared. Okay. v I plus 1 comma j minus 2 vi comma j plus vi minus 1 comma j is equal to 1 over k, right, vi j plus 1 minus vi j. Okay, yes. So when j is equal to 0, right, which corresponds to the initial time, right, all the terms are known except for v I1. Okay, and that's because vi0 is equal to u of xi comma 0. So, but you know u at time 0 is g of xi, so this is g of xi, right? So I'm using this initial spatial boundary condition, right, to initialize the VIOs, all right? And so from that, it's like you can compute the VI1s, okay? So this is the spatial boundary condition. Then I'm going to call this star, right? And then from this, I can compute VI1 from the equation star and these spatial boundary conditions. Okay. All right. So let's write this. So Vi j plus 1 is equal to k over h squared Vi plus 1j minus 2 Vij plus Vi minus 1 comma j plus Vi j. All right. So that's what the method looks like. All right. So you'll see that everything on the right-hand side involves j. So that's the data in the previous step, and then from that you can compute the stuff at the new step. So let's try to sort of draw a picture for this. All right. So what this is more or less saying is that you have the following kind of stencil, right? This is the ij position. This is ij plus 1. This is ij minus 1. This is this is the I minus 1 comma j. And this is the I plus 1 comma j term. All right. So you can see that the terms on the right-hand side involve these three entries. Okay. And if you know those three entries, you can compute this new entry. So you can essentially time march the solution upwards. What sometimes happens is that if you're just adjacent to the boundary, one of these data points in the stencil, it involves the boundary. But you can use what you know from the boundary conditions to fill in that spot. Okay, so nothing happens. Okay, it's a little bit, you've seen something like this. It's like when we were discussing finite difference discretizations of boundary value problems. So the basic idea remains the same. It's like the unknowns are in the interior, and then you can use the boundary data to find sort of the data which is not explicitly included in your unknowns. Okay. All right. Okay, so let me try to rewrite this equation a little bit. Okay, so if I have S is equal to k over h squared, then this equation here becomes the following, that vi comma j plus 1 is equal to k over h squared. Well, actually, let me write it this way. It's equal to s vi minus 1j plus 1 minus 2s vij plus s vi plus 1 comma j. All right, so that's what it looks like. So again, it's easy to convince yourself that this method is explicit, right? It's like the unknown stuff. It's like it's written in terms of stuff on the right-hand side, which you know, either from the data at the previous time interval or the boundary data. Okay, so so this method is explicit, right? So this time marching method. Is explicit. Okay, so so let me just write down the algorithm and then I will stop for now. Okay, so the algorithm is as follows. Right, so you have the following inputs. So you input n, k, and m. M is the number of time steps you're going to compute. So h is 1 divided by n plus 1. And then s is k over h squared. And then wi is g at I times h. And then we let I vary from between 0 and n plus 1 inclusive. And then t is 0. Okay, and then you output 0 the final time, and then w0 to wn plus 1. Okay. All right, so for j equals 1 to, sorry, j equals 1 to m, you do the following. v0 is a at jk, and vn plus 1 is b at jk. So this is just the boundary data on the left and right. Okay, then I do the update for I is equal to 1 to n. You do the following, that vi is s wi minus 1. So w is sort of the data at the previous time, right? Plus 1 minus 2s wi plus s wi plus 1. So you end the do. Then you increment the time. Time is jk. And then you output jt, and then v0, v1, vn plus 1. And then you take the v and you put it in w, because that's where the old stuff was. So w1 to wn, v1 to vn. Then you end the do. Okay, so it's relatively straightforward, right? The first part, initialization, is just specifying the the time step, right? Sorry, the time step. This is the spatial mesh, and then k is the time step, right? And then s is this parameter k over h squared. You first populate, it's like the solution at time 0, it's like with the data, it's like the spatial boundary condition. and then you read off the boundary data on the left and right, right? And then you sort of update the values in the interior using the formula which we saw, right? And then once you've done that, you output the data, and then you replace the data at the old time with the current value so that you can go through it again. All right, so that's all there really is to it. So this is relatively straightforward. It's a simple implementation. And then what we're going to be doing next is to do something about or say something about the stability analysis of the numerical method. So let me just stop here for now.